Hello, everyone. I am honored to present our research titled Physics-Based Hand-Object Interaction via Control Force in Virtual Reality. Our research focuses on enhancing the realism and agency of interacting with virtual objects using our bare hands in VR environments. Interacting with the environment through our hands is one of the most fundamental activities in daily life and represents the most direct and effective means of conveying human intention to the physical world. With the rapid advancement of the metaverse and virtual reality technologies, the demand for precise, physically plausible, and natural interaction methods has grown substantially. Such naturalistic interactions are essential for achieving a high level of immersion and realism in VR experiences. Currently, physics-based hand-object interaction in VR is primarily realized through two input paradigms: VR controllers and motion capture-based approaches. Although controllers offer stable and reliable input, they lack the intuitiveness and natural expressiveness of direct hand movements. For motion capture, one common solution relies on computer vision techniques, such as hand pose estimation from RGB videos. Alternatively, dedicated motion capture gloves equipped with embedded sensors can directly measure hand poses. While such gloves provide more accurate and robust tracking, their high cost limits widespread adoption and broader applications. However, mocap-based HOI faces two major hurdles. First, the difficulty of grasping tiny or thin objects, and second, managing non-continuous contact interactions like throwing. The root cause of these issues often lies in penetration-based dynamics, where the interaction force is proportional to how much the tracked hand penetrates the virtual object. For thin objects, there is simply not enough penetration distance to generate a sufficient force to hold the object, causing it to slip. For throwing, the force builds up too slowly as the hand moves, meaning the object often sticks to the hand instead of being released instantaneously as it would in the real world. To address these limitations, we propose a control-based dynamics approach. Instead of relying on penetration distance, we look at the hand's movement trajectory and velocity. Our framework consists of four main phases: hand tracking, collision detection, control force computation using PD controllers, and cumulative force application via a virtual accumulator. Specifically, the user's hand is first tracked by the hand tracking module, and subsequently, the collision detection module determines whether a collision between the hand and the virtual object has occurred. If collision is detected, our control-based dynamics will compute the applied force according to the hand's past movements. For motion tracking, we utilize Leap Motion Controller, an optical hand tracking system known for its high accuracy. We adopt the skeletal model provided by the device as our underlying hand representation. For collision handling, we distinguish between the tracked hand and the rendered virtual hand to prevent visual interpenetration artifacts. To compute contact points, we adopt a God-object-based approach and utilize a ray-marching algorithm in conjunction with the continuous collision detection module integrated in Unity to iteratively update contact constraints. When computing contact force, we hypothesize that the contact force should be proportional to the hand's displacement and velocity, reflecting the user's intent. For example, if a user clenches their hand faster or deeper, the PD controller interprets this as an intent to apply more force. This mirrors real-world physics much more closely than penetration-based models because it focuses on how the hand is moving rather than just where it is. Specifically, we construct the kinematic chain using modified DH parameters and perform force computation in local coordinate frames. The resulting forces and torques are then transformed into the global frame through rigid body dynamics for subsequent simulation. As the control force can be viewed as an instantaneous force applied to the object, we introduce a virtual accumulator, which acts as a virtual spring without physical volume, to compute the sum of control forces generated throughout the entire contact. The accumulated force is subsequently applied to the virtual object and is computed according to Hooke's law and the principle of conservation of energy. Since control-based dynamics associates the contact force solely with the movements of the tracked hand, which aligns more closely with real-world physics, it enables precise and diverse interaction tasks compared to previous works. We assess the performance of our approach by comparing it to a state-of-the-art penetration force-based approach. In visual comparisons, our method exhibits substantially greater stability when manipulating thin slices, whereas the baseline struggles due to insufficient friction modeling. In object-throwing scenarios, our approach enables clean and rapid release motions. In contrast, the baseline often suffers from undesirable sticking artifacts, which hinder natural and responsive interactions. Next, we conducted a comprehensive user study involving 3 trials. We have recruited 22 participants, including 13 males and 9 females with ages ranging from 22 to 56. Of the participants, 19 are right-handed and other 3 are left-handed. In Trial 1 and Trial 2, participants are asked to pick up the object and place it in a specified area. The object in Trial 1 was a normal-sized cube, while in Trial 2 it was a thin slice. In Trial 3, participants had to pick up the object to a certain height and throw it a specified minimum distance. After each trial, participants were asked to answer questions regarding their subjective assessments of the sense of agency for the 2 methods, which is rated on 11-point Likert scale. We use Wilcoxon tests for the analysis. The first set of questions comprised statements A1 and A2. Statement A1 was defined as, I felt that the hand-object interactions were realistic and natural, corresponding to the null hypothesis that the interactions are equally realistic and natural when using both methods. Statement A2 was defined as, I felt that the outcome of the hand-object interaction met my expectations, with the associated null hypothesis that the outcomes of hand-object interactions for both methods meet participants' expectations equally. The hypothesis testing results indicate that our approach achieves comparable performance for pick-and-place tasks involving objects of regular size, while demonstrating significantly superior performance in scenarios involving thin objects and object throwing. After completing all trials, participants provided an overall evaluation of the 2 methods based on statements A3 and A4 and indicated their preferred approach. Statement A3 was defined as, I felt that I could control the virtual hand, corresponding to the null hypothesis that both methods have equal controllability. Statement A4 was defined as, I felt that I could interact with the object as I intended, with the associated null hypothesis that interactions with both methods equally satisfy participants' intentions. The hypothesis testing results demonstrate that our approach achieves significantly superior controllability and better aligns with participants' interaction intentions. Furthermore, 80% of participants selected our method as their preferred approach. Finally, we present additional visualizations beyond the interaction scenarios included in the comparative evaluation, such as transferring, holding, slapping, pushing, and grasping slender objects. That concludes our presentation. Thank you for your time and attention.